All right, so we're going to go over the explanation of the free response problems that were assigned for homework for tonight. And I'm going to start with the problem we did not get to in class today, which this is the second problem that was shown in the agenda for February the 9th. All right, so this is classwork problem free response question number 2. So let's take a look at how to handle a problem like this one. So it says you have a sample containing 2/3 of a mole of potassium chlorate. Heated until it decomposes to form potassium chloride and oxygen gas. The oxygen is collected and inverted in an inverted bottle through the displacement of water. So they're telling you it was collected by water displacement. Answer the following questions using the information. So again, this is a multi-part. This will be called a long free response question. So for part A, it wants us to write a balanced chemical equation for the reaction. So they gave us the formulas that we need. So it says it was decomposed. So we're going to write the KClO3. And potassium chlorate is a solid. It is a salt, an ionic compound. That's how we know it's a solid. And it says it decomposed as it was heated. And it formed potassium chloride, KCl, which is another solid because, again, it's a salt. It's an ionic compound. And then oxygen gas, so O2. So here's the gas that's formed. And so it says the oxygen was collected and inverted in a bottle through water displacement. So we're going to keep in mind that we are going to have to subtract out the water vapor in just a little bit. Now, to get the balanced chemical equation, you got to come back here and watch your coefficients. So we see that we have 2 oxygens here and 3 here. So we should multiply this by 2. That's going to mean we need a 2 here and a 3 here. So that will be part A for this long free response. Let's look at part B. So it says calculate the number of moles of oxygen gas produced. Now this is kind of odd, I realize that, but that they give it to you in a fraction form. So you could say 2 divided by 3 to get the actual moles, but I think you'll see in just a second kind of why they gave it to you in fraction form, because the numbers are supposed to be pretty easy to work with. So let's just say if you were to write it as 2/3 of a mole, so 2 over 3 moles, and that's of the KClO3. And so, of course, that's a fraction, right? So we do have a denominator here, but we want to know how many moles of oxygen that is. So we have our balanced equation. So this is a stoichiometry problem. So you're going to put your moles of KClO3 on bottom and your moles of oxygen on top. So that's going to be a 3:2 mole ratio. Now, notice what happens here. So if you just look at the numbers, the 3 cancels with the 3 and the 2 cancels with the 2. So it's going to give you exactly 1 mole of oxygen. Now, alternatively, if you had have said, well, 2 divided by 3, plug it in the calculator, that does give you 0.67 moles, of course, and then you do the same thing, a 3 over 2, and I'm not going to put the units in there, but you see it's the same as up here. And that would, if you plug that in your calculator, you would get 1 mole of oxygen. Okay, so either way, you get 1 mole of oxygen. And as far as sig figs goes, since they just gave you it as a fraction, I would just keep it 1 sig fig. That's not that huge of a deal on this particular problem, really. All right, let's look at part C. So part C says the temperature and the pressure of the sample are adjusted to standard temperature and pressure. The volume of the sample is slightly greater than 22.4 liters, and it wants you to explain. So let's just think about what they're telling us. They said that they collected this by water displacement. So keep in mind that if you're collecting a gas in your gas collection bottle, and so of course you have your water here, and the gas is up here. So the gas collected was oxygen, right? Well, since the water is here in your gas collection bottle, we said that there will be water vapor also, right? So you have your water vapor and you have your oxygen gas collected. Because anytime collected gas over water by water displacement, you're going to have to apply Dalton's law of partial pressures. So keep in mind, you don't have just the pure gas here, and that's what you have to understand here. So, at standard temperature and pressure, we know that for sure, for any gas, the volume, so this is kind of what you would want to say, the volume of 1 mole of oxygen should be 22.4 liters. And that's just because of molar volume definition at STP. They're telling us here that the actual measured volume, so I'm going to say but the volume is greater. They're telling us that in the problem. And the reason is because, look, it's not just oxygen here. So there's a mixture of gases. So it's greater because the oxygen is not the only gas present. Or you could say because the oxygen isn't pure. And the reason is since it was collected by water displacement. The water vapor, so the gaseous water, is also present. So the presence, so you could just say the additional gas leads to a larger volume. Okay, so basically it's because there's more than one gas there. It's not just one gas. Okay, so that would be a sufficient answer for part C. And again, keep in mind that you want to be thorough with your answers. I'm sort of abbreviating this here. And now on the unit test for me, of course, I would be able to take abbreviations, but on the actual AP final exam or AP Chem exam, you would not want to abbreviate too terribly much. All right, let's look at part D. Part D says, an excess of sulfur is burned in 1 mole of oxygen. Okay, I know you can't see that, so you're reading along. I'm reading from up top here. So it's an excess of sulfur burned in 1 mole of oxygen. So that was the oxygen gas that was collected in the presence of a catalyst. So of course that's going to speed it up. And it says to form gaseous sulfur trioxide, SO3, write a balanced chemical equation, and then calculate the number of moles of gas formed. So again, they told you, so you're just kind of taking the word equation. So it says you have an excess of sulfur, so S, and sulfur is a solid, okay, the element sulfur. So an excess of sulfur was burned in 1 mole of oxygen, so you'll say plus O2, okay, so the oxygen that was formed, and oxygen, of course, is a gas at normal conditions. And it said it was catalyzed to form gaseous sulfur trioxide. So they're telling you that's a gas, just in case you didn't know. Okay, so that's another gas that's formed. Write a balanced equation. So we're going to balance this equation. So you'll notice here you have 2 oxygens here and 3 here again. So we're going to multiply this by 3 and this by 2. And that gives you 2 sulfur. So put a 2 there. So you get a 2, 3, 2 again for that equation. But that's not all they want you to do on part D. It wants you to also calculate the number of moles of gas formed. Well, keep in mind, they told you that it was 1 mole of oxygen that reacted with excess sulfur. So that means the oxygen is the limiting reactant because they told you the sulfur was the excess. So you know how much oxygen you started with. So 1 mole. And again, sig figs are not really important at this point because they didn't give you the actual number. They just said the word 1 mole. And so now you're just going to do a little stoichiometry. Okay, so you need moles of oxygen on bottom, and you need moles of the SO3 on top. And so you'll notice that's a 3 to 2 mole ratio. So you put 2 over 3, and that's going to let your moles of oxygen cancel, and then that's going to give you 2/3 moles of SO3 or 0.67 moles of SO3. So that's the answer to part D. All right, one last part here. So for the last part of this question, it says, after the sulfur had completely reacted, so after this sulfur has completely reacted, a sample of the residual water was removed. So there must have been some water vapor that was produced there also. So a sample of the residual water was removed from the bottle and was found to be acidic. Explain with a balanced chemical equation. Okay, so as far as that goes, that's part E. I don't know if I can squeeze all this in. Hopefully I can. This is something that we'll talk about in more detail in the acid-base unit, but we will learn that if you ever have a non-metal oxide, so I'm just going to put here a non-metal oxide, whenever it dissolves in water, it's always going to produce an acid. Okay, so the equation, and again, we'll talk about this. This would not be something I would ask you for this unit test, but when we talk about the acid base unit, we're going to learn about metal oxides when they dissolve in water, what forms, and when a non-metal oxide dissolves in water, what forms. But anytime you have a non-metal oxide dissolving in water, H2O, then it's always going to form an acidic solution. So in this case, it's going to form sulfuric acid. This is what happens with acid rain. H2SO4, and that will be aqueous. Okay, and that is balanced. Okay, so 1, 1, 1. So that's it. So that's the work for the first FRQ. All right. Now let's take a look at the next question you had. So for the next question, this was actually in the homework part of the module. Notice they gave you a graph that has the pressure and the temperature shown, and they have two gases. So this is a mixture of gases. And it says the graph above shows the changes in pressure with changing temperature of samples of gases of helium and argon confined in a closed 2-liter vessel. So they're both, in a closed container. So you have your mixture of argon and helium. So of course we're talking about Dalton's law of partial pressure. So this is a mixture of gases. So it says for part A, what's the total pressure of the two gases in the container at a temperature of 200 Kelvin? So now you're going to kind of be estimating here, so you're going to kind of pick, and I've tried to go ahead and draw the line, so I tried to pick approximately where you think 200 Kelvin is, and this would be something you could estimate, but if you read up and over, so this will be the pressure, you read over, that's approximately 1 atmosphere for the helium, and then you keep reading up to where it intersects the argon, and you're going to read over, and that's, I would estimate that's around 1.5, okay? So for part A, you're just kind of using Dalton's law of partial pressures here, right? So you're just going to understand that the P total is equal to the partial pressure of argon plus the partial pressure of helium, which is going to be essentially 1.5 plus 1 atmosphere. And so that's going to give you the P total in the container. So the total pressure in the container would just be around 2.5 atmospheres. And of course, you are doing some estimation on that one, so there'd be some leeway with that. Now for B, it says how many moles of helium are contained in the vessel? I don't have a lot of room to do that part, so I'm just going to bring some more paper right here. So for part B, how many moles of helium are contained in the vessel? So when you see moles, you want to think the ideal gas law, okay? So let's just kind of write down what we know, PVNRT. So it wants to know the moles of helium. So I'll put N of He. All right. And going back to what they've told us so far, so the pressure for this particular, and again, we're at 200 Kelvin is the temperature in question. We know our R, 0.08206. And so we said for the helium that will be about 1 atmosphere. And they want to know the moles, and so we have everything we need except so we need to know the volume. And so for the volume of this, they told us that the container was a 2-liter vessel, 2 liters. And again, as far as your sig figs go, you know they didn't give you definite numbers here, so just that's the one sig fig number. Wouldn't worry so much about sig figs on this particular part. So we're going to solve for moles. So the moles of helium, N is going to be equal to PV divided by RT. And so that's going to give you, plugging in 1 times 2.0 divided by 0.08206 and 200. And so that's going to allow you to get your moles of helium. And that, if you plug it into your calculator, 0.12 moles. And a good rule of thumb, especially for the AP Chem free response questions, a good rule of thumb is going like to 2 to 3 sig figs on questions like this. So it's typically good to go 2 to 3 sig figs. All right, let's take a look at part C. For part C, it says how many molecules of helium are in this vessel. So all we got to do is use Avogadro's number, right? We know our moles. So we're going to start with our 0.12 moles of helium. And we're going to get, using Avogadro's number, 6 times 10 to the 23rd, or 6.02 times 10 to the 23rd. And that would be molecules equal to 1 mole. So you're going to multiply by Avogadro's number. And again, I would just go to 2 sig figs on this. So that's going to give you 7.3 times 10 to the 22nd molecules. Now, to be accurate, I would have chosen the word atoms because helium is not diatomic. It is just an atom of helium. But I'm going to, if you put atoms, I'm sure they would count that because technically that is the better choice of your unit there. All right, D. Molecules of which gas will have a greater distribution of velocities at 200 Kelvin? So you think about the velocity. We talked about root mean square velocity. You can kind of look at that. And you could also think in terms of Graham's law. They're both at the same temperature. But if you do the Erms equation, the root mean square velocity for, I'll do the helium, and then, of course, I'll take a look at the argon. So if you do the Erms equation for the helium, you're going to have square root of 3 times, remember, it's RT, so that's 8.3145. You got to use the joule per Kelvin mole. This is 200 Kelvin is your temperature. And remember, for the Erms equation, you've got to have your molar mass in kilograms per mole. So for helium, that will be 0.00400. And if you do the same thing for the argon, you'd have 3 times the 8.3145 times 200, and then divided here by your molar mass of argon in kilograms per mole. So that's going to be 0.03995. And again, that's kilograms per mole. So if you were to solve for the root mean square velocity, you can get the actual value here for the helium. You've got 1,116 meters per second. And for the root mean square velocity at the same temperature for the argon, you get only 353 meters per second. So hopefully you could kind of tell that helium, being such a lighter molar mass, is going to travel a lot faster if they're at the same conditions. You could have compared also them, you could have used Graham's law to justify that. So as far as having the greater distribution, since both gases are at the same temperature, they actually technically have the same average kinetic energy, but the molecules of helium have a higher average velocity. So you would say the molecule, and I don't think you would even, on the AP test, you wouldn't even have to go to this point. You could just say, due to the much lower molar mass of helium, since they're at the same temperature, the helium atoms. So you could say the molecules of helium have a greater average velocity, that's your speed, because they have a lower molar mass. You could say, as proven with the root mean square velocity equation above. Okay, so again, that's justifying your answer. You always want to be able to justify your answer. All right, part E on this one. Part E said, if the volume of the container were reduced to 1 liter, so you go from 2 liters to 1 liter at constant temperature of 300 Kelvin, so they've increased the temperature, what would be the new pressure of helium? So, you're looking here at P1V1 equals P2V2. So don't try to complicate it. So your original pressure for the helium was 1.5 atmospheres, and your original volume was 2.0 liters. The P2 is what you're looking for, and the V2, they said they changed the volume to 1 liter. Okay. So for this one, you're going to divide both sides by 1, and that's going to solve for P2. So that will give you, if you plug in 1.5 times 2 divided by 1 is 3.0 atmospheres. And that finishes up this free response number 2. Oops, 3.0 atmospheres, so you can see that. Okay. All right, the last homework problem that you had to do. Okay, so you were given a chemical equation, KClO3. So this is the exact same equation that we had in the classwork example, but it's a little different situation here. So it tells us that we have the reaction above took place at 1.45 and 1.45 liters of oxygen gas were collected over water. So this is a collected over water problem. At a temperature of 29 degrees Celsius, pressure of 755 millimeters of mercury. The vapor pressure of water is at 29 degrees Celsius is 30 millimeters of mercury. So I want to know what's the partial pressure of the oxygen gas collected. So for that one, for part A, so the partial pressure of oxygen, you're just going to subtract off the water vapor. So you're going to take the P total, which is P total minus the pressure of water. So the P total was 755 millimeters of mercury. And the vapor pressure of water at this temperature was 30.0 millimeters of mercury. Okay, so when you subtract, you're going to round to the nearest whole number, because when you add and subtract, remember, you go least decimal places. So when I subtracted that, that gave me 725 millimeters of mercury. So there's your pressure in millimeters of mercury. Now, it does not specify the unit, so you can leave it in millimeters of mercury for part A. That will be fine, but I'm sure if you converted it to atmospheres, that would certainly be acceptable. All right, part B. How many moles of oxygen gas were collected? Okay, so when we see moles, we want to think Pivnert. So for part B, I'm going to list my givens, PV and RT. Remember to always show your work. So you're looking for the moles of oxygen gas collected. So we know R, 0.08206. They told you the temperature here was 29 degrees Celsius. You're going to add 273.15 to that. That'll give you 302 Kelvin. The volume here was 1.45 liters, and it's in liters, so that's the right unit. And the pressure, now we do have to convert that to atmospheres, right? So we're going to say 725 millimeters of mercury divided by 760 to get it to atmospheres. and that needs to be to 3 sig figs, so 0.954 atmospheres. That's what you get for that one. So now we're going to solve for moles. N is equal to PV divided by RT. So we're going to substitute in 0.954 times 1.45 divided by the 0.08206 and the 302. And that'll give you your moles. Plugging that in, I got 0.0558 moles of oxygen for part B. All right, for part C, it says, what would the dry volume, okay, so taking off the water vapor, what would the dry volume of oxygen gas be at a pressure of 760 millimeters of mercury and a temperature of 273 Kelvin? So notice that they want to know the dry volume. They're giving you another pressure and a different temperature. So notice how the pressure and temperature is changing. So for part C, you're going to think in terms of another gas law. You're going to think in terms of P1 V1 over T1 equals P2 V2 over T2. Now, for the P1, we're going to use the 0.954 because that's the oxygen that's dry, right? That's the pressure of the oxygen dry, 0.954. Let me try to substitute this in. I'm going to substitute it in here. So 0.954 atmospheres. And the volume that we had initially, the first volume was 1.45. That was the volume that was collected, and that's liters. And then the temperature initially was 302. So we're using those first conditions. But now they're wanting to know what is the dry volume if you have STP. Pretty much. So you have 760 millimeters of mercury, which is, again, an atmosphere is 1 atmosphere. V2 is what you're looking for. And with the new temperature, which is 273 Kelvin. So you're solving for V2. I don't have a lot of room here, so I'm just going to go, cross multiply. You're going to isolate your variable for V2. So for part C, you would get 1.3 liters. That would be the volume of that dry gas at STP. All right, one last part to do. Part D. What's the mass of KClO3 consumed in this reaction? So I'm just going to do this up here. So part D, because I got room up here. All right, so you've got the chemical equation. You want to know the mass. So keep in mind, we found the moles of oxygen here. So we know the moles from part B. So we're just going to start with that, 0.0558 moles of oxygen. And since we have that chemical equation to relate it, we can use the mole ratio and the molar mass. So according to this equation, 2 moles of the KClO3 will react with 3 moles of the oxygen. And now we need the molar mass of the KClO3. And so for that, if you add up the potassium chlorate's molar mass, I got 122.55 for that. And that lets the grams of KClO3 cancel. I'm going to round that to 3 sig figs. That gave me 4.56 grams of the KClO3. Okay? All right, so those are the solutions explained for last night's homework. Hopefully that helped. And if you have any other questions, please message me in the inbox and I will talk about them in class right before we take our FRQ today.